In the last module, we had been looking at regression models with unobservable variables. So, if you have unobservable variables, very often we take recourse to what are referred to as proxy variables, which stand in for the unobservable variables. So, again, sometimes what you have is, even if the variable is observable, they may be contaminated with error. So, we have error contaminated variables or errors in variables. And we saw that in either of these two cases, the ordinary least squares cannot be applied, because that would lead to inconsistent estimators, not only for the variables which are contaminated with error, but also for the variables or the coefficients which are not contaminated with error. So, overall the estimation cannot be carried out, because the estimators would be biased in small samples and inconsistent even for large samples. And we have seen that if we drop such variables, proxy variables, if we have errors in variables and we drop these variables, even then there would be some bias in the model, bias in the parameters that of the other variables that are there in the model. So, we cannot get rid of this problem by using the OLS in one way or the other. In this and the next lecture, we will be talking about methods for estimation when there is the presence of either proxy variables or there are errors in variables. There are primarily two methods for estimating the parameters of a model, which has either proxy variables or error contaminated variables. So, as we saw, the least squares are ruled out, but then we can use the maximum likelihood method, and the second method that we will be discussing later would be the instrumental variable technique. In today's lecture, we will be looking at the maximum likelihood method of estimating the parameters in the presence of proxy variables or errors in variables. Now, let us illustrate the problem through a two variable model. So, let the actual model be yi star is equal to beta naught plus beta 1 xi star plus ui. Ui is the model error, and yi stars and beta xi star are the true values of the response and the explanatory variables respectively. So, this is the actual model that we want to study. Now, both this yi star and xi star cannot be observed as it is. So, what we observe is yi, which is yi star plus vi. Vi is an error. So, yi is error contaminated, yi star is true and yi is error contaminated. Similarly, instead of xi star, we observe xi, and xi again is error contaminated, the error in this case being wi. So, ultimately what we observe is the model yi is equal to beta naught plus beta 1 xi plus epsilon I. Now, this error epsilon I actually is composed of the model error ui plus vi minus beta 1 wi. Remember, this is the reason why this xi and epsilon I gets correlated, and we have a problem of inconsistency if we are using the OLS estimator. Now, since we are using the maximum likelihood estimator, we need to make certain distributional assumptions of the errors. Let us assume that the ui's are IID normal 0 sigma u square, the vi's are IID normal 0 sigma v square, and the wi's are IID normal 0 sigma w square. We will also assume that xi star itself is stochastic. Of course, if it is non-stochastic, we can always take it out, but let us take the more general case of xi star being stochastic, and we will assume that xi star is also normal, it has a mean mu and its variance is sigma x star square. And we will assume that this ui, bi, wi and xi star are all independent of each other. So, there is no correlation between the different errors and also no correlation with the explanatory variable. Now, given this setup, observe that xi is xi star plus wi, that is what we have already. But if you look at yi, and we can write yi in terms of xi star, in that case yi will be equal to beta naught plus beta 1 xi star plus ui plus vi. And under the assumption of normality, because all these variables, now you see that xi and yi are written in terms of all the variables whose distributions we know. So, under the normality assumption, we have xi and yi jointly distributed as a bivariate normal, with mean of x being mu, mean of y being beta naught plus beta 1 mu, variance of x being sigma x star square plus sigma w square, mean of y being beta 1 square sigma x star square plus sigma u square plus sigma v square. All this comes from this xi and yi, and if you take the covariance between xi and yi, it comes out to be beta 1 sigma x star square. So, we get a normal bivariate normal distribution with these as the parameters. Now, in the usual case, if we have xi yi as a bivariate normal with mean mu x, mu y, sigma x square, sigma y square and rho, we can write the standard log likelihood as minus of n log twice pi minus n by 2 log of sigma x square sigma y square 1 minus rho square to the power of half minus half summation I equal to 1 to n yi minus mu x by sigma x whole square plus yi minus mu y by sigma y whole square minus twice rho xi minus mu x by sigma x into yi minus mu y by sigma y. And by standard procedures, you know that the ML estimates would come out as mu hat x would be x bar, mu hat y would be y bar, which are the sample mean and the sample mean of x and y respectively. Sigma x square would be the sample variance for x, sxx, sigma y square would be the sample variance of y, which is syy, and sigma xy would be the sample covariance sxy. Remember that sxs and syy as well as sxy all will have a denominator of n. So, it is divided by n and not by n minus 1. We know that the ML estimates are not going to be unbiased. So, there will be a this n minus 1 is taken for this unbiasedness, but the ML estimates has a divisor of n. Also notice something, that even if we had not assumed normality and if we had been doing the method of moments, these are exactly the estimators of these parameters that would have come. So, what we are doing basically is we are equating the sample moments with the population moments. So, the moment estimators also would have led us to the same estimates in this case. So, this is a standard result that we have from the bivariate normal distribution and its ML estimates. Let us go back and look at our problem. So, if we look at what is mu x for us, the mean of x is mu. So, mu must be equal to x bar, that is the first equation. Mean of y is beta naught plus beta 1 mu. So, that must be equal to y bar. Variance of x is sigma x star square plus sigma w square, that must be equal to sxx. Similarly, sigma u square plus sigma v square plus beta 1 square sigma x star square must be equal to syy. And finally, the covariance beta 1 sigma x star square would be equal to the sample covariance sxy. So, what we have here is there are 5 equations. But if you look at the number of parameters, you have mu, beta naught, beta 1, sigma x star square, sigma w square, sigma u square and sigma v square. So, we have 7 parameters or 7 unknowns. but then we cannot solve these 7 unknowns from these 5 equations. Of course, we will need to put some restrictions so that we can get a solution to these unknowns, and the restrictions must be 2 so that we can get unique solutions. Now, before we go and look at the type of restrictions that we would need to put in, notice something. Notice the 4th equation here. You will find that in the 4th equation we have sigma u square plus sigma v square, and these two terms do not come in anywhere else. So, what happens is that we cannot eliminate one and estimate the other. So, whenever we try and estimate this from the 4th equation, suppose we know SYY, suppose we know beta 1, and suppose we know sigma x star square. So, SYY minus beta 1 hat square sigma x star square, that will give us sigma u square plus sigma v square, and we will be unable to separate these two. So, we cannot estimate these two separately. Hence, what is generally done is that we assume that sigma u square is equal to 0. And what does that mean? It means that mind you, sigma u is the variance of the model error. So, we are assuming that the true model is exact, it does not have an error. And when we look at the observed model, the error comes in primarily through the y error, that is sigma v, or rather v, and it comes in through w as well. So, we assume that the true model is error free, and hence the number of parameters now reduces by 1. So, we have still 5 equations, but we have 6 unknowns. So, we still need one other restriction to make. So, let us look at what type of restrictions we have. Generally, 4 very standard restrictions that are made. The first of this is we assume that sigma w square is equal to a constant a. What is sigma w square? So, we are saying that we know the error variance for the explanatory variable. If we know sigma w square equal to a, then you can use equation 3 and put this a value to get sigma x star square hat as sxx minus a. And then if we use this in equation 5, then we have beta 1 hat is equal to sxy by sxx minus a. And once we get beta 1 hat, we get all the remaining terms. In fact, from 4 we get sigma b square is equal to syy minus beta 1 hat square sigma x star hat square. And of course, we do not need to look for mu separately, because the first equation it gives us mu hat is x bar always, it is already defined. And if you look at the second equation, knowing beta 1 hat, beta naught hat would be y bar minus beta 1 hat x bar, because mu is x bar. So, if we take the condition that sigma w square is equal to a, we can estimate all the other parameters. Let us look at the second case. Here we will assume that sigma b square is known to us and it is equal to b. What is sigma b square? It is the variance of the response or the error in the response. Then from 4, using this sigma b square equal to b, we get that beta 1 square sigma x star square is equal to syy minus b. And then dividing 4 by 5, beta 1 hat turns out to be syy minus b by sxy. And then of course, once you have got your beta 1 hat, as before, you can get the other terms as well. So, it will be precisely as before. Just notice something, if in either case say sigma w square is equal to 0, if a is 0, that means we have a x variable which is not contaminated with error. And you can see that in that case we go back to the usual regression estimates. Similarly, if b is equal to 0, we will have a response which is not contaminated with error, and we will be going back not exactly to the same estimates, because mind you, the problem comes in when you have errors in the x variable. but we can use this method to get an estimate of beta 1 hat. But for the first case, of course, you would be going back to you can use the ordinary list squares. Let us look at the third case. Sigma x star square by sigma x square is equal to c, and c is a known constant which is less than 1. Now, why is it less than 1? This is because sigma x square, the denominator, is primarily the sum of sigma x star square plus sigma w square. So, this c is equal to sigma x star square by sigma x star square plus sigma w square, and hence must be less than 1. And if you solve this, we will find that sigma w square would come out to be 1 minus c by c into sigma x star square. Now, one advantage of this third case over the first and the second is that in the first and second case, we have to have some idea of what the error variance is like, and very often this is difficult to gauge. In the third case, we are not saying exactly what the variances are to be like. We are only saying that sigma x star square by sigma x square is c. Suppose c is 0.8. We will say that 20% of the variability is because of the error sigma w square and 80% because of the true value. So, we are just saying how much of the true value is contained in the variable that we are measuring and what proportion of it is error. So, we are talking in terms of proportionality, and hence it is easier to conceive than the exact absolute value of this variances being equal to some particular value. Now, let us come back to this. We have sigma w square is equal to 1 minus c by c sigma x star square. And if we use 3 and substitute sigma w square there, then we have sigma x star square coming out as c times s x x. And from 4, or in this case rather it comes from 5, beta 1 hat with the sigma x star square already obtained, it comes out to be s x y by c x x. So, once we have got beta 1 hat, we can get the other parameters as before, and hence we can get estimates of all the 6 parameters. Now, let us come to the fourth case. In the fourth case, we assume that sigma v square by sigma w square is equal to some known constant lambda. Now, again this is a plausible assumption, and we are saying that the error variables for the response by that variance for the explanatory variable, this proportion is known to us. So, we are not giving exact values of sigma v square, sigma w square, we are only saying that one is equal to the other or maybe twice the other, etc. So, it is just a proportionality idea that we are using, and this is much more easier to conceive than getting the exact values of this variances. Now, once we can assume this, very often the data tells us what it should be like, but once we can assume this, if we use and substitute sigma v square in equation 4, then writing sigma v square as lambda times sigma w square, we can get this as lambda sigma w square plus beta 1 square sigma x star square is equal to s y y. Now, subtracting lambda times equation 3 from this, we have beta 1 square minus lambda times sigma x star square is equal to s y y minus lambda times s x x. And then if we use 5 to replace the sigma x star square in this equation, we have beta 1 square minus lambda s x y by beta 1 is equal to s y y minus lambda into s x x. And this would imply that if you take the beta 1 in the denominator on the right hand side, bring all the terms to the left hand side, we have s x y into beta 1 square minus s y y minus lambda s x x whole thing into beta 1 minus lambda s x y, which is equal to 0. So, you notice that this is a quadratic in beta 1, and we can solve this quadratic and get estimates of beta 1, and this comes out as beta 1 hat is equal to, remember the formula, it is minus, if you have a x square plus b x plus c equal to 0, then the solution should be minus b plus minus square root of b square minus 4ac by twice a. So, in this case beta 1 hat would be syy minus lambda sxx plus minus square root of syy minus lambda sxx whole square plus 4 lambda sxy square divided by twice sxy. So, we get two solutions. Notice that in the numerator, just concentrate on the numerator, if you look at the term within the square root, it is syy minus lambda sxx whole thing square plus 4 times lambda, which is positive being the ratio of two variances, into sxy square, which is again positive. So, we have the square term plus a positive term, and if you look at the first term is the square of the first term within the square root. So, the square root should be coming out to be, because it has a positive term attached to it, would come out to be larger than the first term. So, one of the solutions should be negative, because when you subtract the larger term, it will give you a negative value, and the other term you are just adding it, so it will be positive. So, one of the terms is going to be negative and the other term is going to be positive. So, which of the two solutions of beta 1 hat should you be taking, the negative one or the positive one? In this case, it is easy to understand that, remember what is beta 1? Beta 1 is the slope of the regression of y on x. Now, if y is increasing with x, then the slope is going to be positive, and if y is decreasing with x as x increases, then this slope is going to be negative. But then if y is increasing with x, covariance sxy would be positive. If it is inversely related, then sxy is going to be negative, and we have the sxy value. So, if sxy is positive, take the positive value of solution of beta 1. If sxy is negative, take the negative solution of beta 1, and that would be the solution of beta 1 that you get from this quadratic, and that would be the one that you should be using. So, once again, if you get beta 1, then you can get the remaining parameters, and you can solve all the equations and get all the unknowns. So, these are 4 cases that we have been looking at. There may be some other cases that you have in particular situations, but primarily the two most popular methods is to make assumptions, either the 4th case or sometimes the 3rd case as well. So, you either make an assumption on the ratio of the two error variances or on the variance of the true value of x by the variance of the actual observed value of x, because these are proportionality type of restrictions, and it is easier to make this, and you can solve your betas. And you know that if you get your maximum likelihood estimators here, all the properties of the maximum likelihood estimator would hold in either of the two cases. In today's module, we had been discussing methods of estimating the parameters in the presence of either proxy variables or in the presence of error contaminated variables. There are two methods that we generally use. One is the usual maximum likelihood method, and the other is the errors or the instrumental variables. Today we discussed the maximum likelihood method, and we saw that even the direct application of the maximum likelihood method does not yield all the parameters, because there are too many parameters compared to the number of equations that we get, and we need to put some restrictions. We saw how we can actually reasonably get some restrictions and estimate the maximum likelihood parameters through the maximum likelihood method.